All right, guys, you can see today's lesson on periodic properties of the elements, otherwise known as periodic trends. For a lot of you guys who had me last year, this is going to be a lot of review, so I think this will be good and maybe easy. Hopefully I'm just going to help you recollect what you already learned. It says, this chart represents the difference between the percentage of people thinking about pi 10 seconds ago compared to now. So no one was thinking about pi until he talked about pi, and on a get it pie chart, get it. Periodic table developed back in the 1800s. It says they're organized more so on chemical properties. That is how they react with other atoms, not so much physical properties like melting points, boiling points, things like that. So this is kind of showing when different elements were discovered. We'll move on. What was pretty remarkable was, like Mendeleev, what he did was so remarkable. Like back in the day, here's the periodic table. I'm just not switching to it because it takes too long. There was germanium. Germanium was not known back then, but he actually left a space in his periodic table, assuming that germanium sometime after would then be discovered. And he actually predicted some properties, some both physical and chemical properties, and looking at those values compared to the actual values of germanium, which was discovered sometime after, 15 years or so after, it's remarkably similar. Okay, so you guys, we're going to look at some things like size of atoms, a term that you guys should have remembered from last year, ionization energy, and electron affinity. Otherwise, we can use the term electronegativity. That's probably what you're familiar with. Okay, so electrons are both attracted, notice in purple here, effective nuclear charge. Electrons are both attracted to the nucleus and repelled by other electrons. Guys, I want to show you guys this. You guys remember thinking about magnets, right? We can liken these just like north and south poles have an attraction for each other. Do that. Right? See, they have. Okay, they're not very strong magnets. Okay, you guys, we can liken this to protons and electrons, right? Opposite charges attract. So just think about that. And then you guys think about it. What is going to affect the force of attraction between positive and negative charges, protons and electrons? And you guys agree what's going to affect the force of attraction? Wouldn't the distance between them, right? When you guys agree, the further the distance, the less the attraction. But as the distance between those charges decreases, the force of attraction is greater. There's one other factor that affects the force of attraction between oppositely charged particles. Not only the distance between them, but you guessed it, the size of the charge. So imagine if I had more protons or more electrons. What would the effect on the force of attraction be? Wouldn't it be greater? Right. So you remember those two factors can be shown with Coulomb's law. Here's Coulomb's law. I know it looks kind of funky, but you guys here, F is the force of attraction. You guys can imagine, what are Q1 and Q2? That's the size of the charge. And you guys would agree, look, that's in the numerator. So wouldn't you guys agree, if I increase the size of the charge, like I used a larger magnet, if you increase the size of the numerator, wouldn't you increase this overall size of the whole value, thus increasing the force of attraction, right? So this is just a mathematical representation of what we were just observing. R, that is the distance between those charges. And you guys see, where is the R factor? It's in the denominator. And you guys would agree, if you increase the denominator, right, so we increase the distance between, if the number on the bottom increases, what happens to the overall value if you divide by a larger number? Doesn't the overall value become smaller? And that agrees with what we had just observed. The greater the distance between those charges, the less the force of attraction. And then K, anytime you guys see a small k, that's just a constant that's used to make the equation work. So that's just a constant. We don't really focus too much on that. Okay. The nuclear charge that an electron experiences depends on both, right, its attraction to the nucleus and also the repulsion due to other electrons in its vicinity. You guys were talking about the size of an atom or atomic radius. So how that's measured is, if we saw two atoms bound together, we would basically take the distance between the two nuclei and then we would just half it, and then that's what we would use to define atomic radius. Okay, atomic radius. From left to right in the period, you guys remember we did this last year. So if we were to go from left to right in a period, so we just choose a period on our periodic table, as we go left to right, do the atoms get bigger or smaller? You guys remember? the atoms, in fact, I would draw this, the atoms actually get smaller as you go left to right. That's a downward arrow. I don't know if you guys can see it. Now that's due to, rather than just memorizing that, because you'll have a tendency to forget, it's always good to know. Why would they get smaller? Well, you guys think about it. I'll just go lithium over here. I'm just going period 2. Lithium has a atomic number of 3. That means it has 3 protons. Whereas fluorine all the way on the right has an atomic number of 9. I don't know if you guys can see it. It's a +3 and a +9. What might explain why they get smaller? When you guys agree? Well, if you have more positive protons in the nucleus, won't those have a stronger force of attraction on the outer electrons, pulling them in, making the atoms in general get smaller as you go left to right? So an increase in the positive nuclear charge. Okay, top to bottom. What happens to the size of atoms as you go from top to bottom in a group? So let's say we're going down from, let's say, lithium down to francium. What do you guys expect to happen to the size of the atoms? Contrary to the previous explanation, they actually get bigger. You guys ought to draw that. That's going to be a lot easier to remember than just even putting this. They actually get larger. What might be the reason for that? Despite the fact that you do have a greater atomic number, that's why maybe some of you guys might have predicted they get smaller using the same reasoning here. But a greater factor that impacts it, you guys should know, as you go down, you guys remember in the periodic table, each period corresponds to a shell of electrons. So as you go down, you're getting increasingly more and more shells of electrons. And you guys remember what those underlying shells of electrons do to the attraction between the nucleus and the outer electron. Doesn't it reduce it? Think about it like this, guys. Let's say this is my nucleus. I don't know if you guys can see a large magnet. And this is my outer electron, right? There's a force of attraction. Obviously, this is orbiting it because it has an attraction for the nucleus. Well, what if we have, you remember this is our valence electron in the outer shell, but we'd have underlying shells of electrons. So let's say I have one underlying shell of electrons. We call those the core electrons. What does that do to the force of attraction? Doesn't it lessen the force of attraction? And then just imagine more and more shells of electrons that are between the valence electron and the nucleus. What do more and more shells? Just imagine these are shells. What does that do to the force of attraction? It even makes it even less. And therefore, if there's less force of attraction, wouldn't you guys agree that outer electrons are not pulled in as closely? They're freer to move further out, and therefore that would explain why the atoms actually get larger. Okay, hopefully you guys, this is just reminding you of things that we had learned last year. We call that the screening effect. The idea that there's increasing number of shells of electrons. Okay, underlying shells of electrons screen out some of the attraction that the outer electron has for the nucleus. So you guys remember some terms, cation, that's what we use to describe a positively charged atom. You remember, it's the metals that tend to lose electrons and become cations. Anions are atoms that gain electrons and thus become negative. Okay? And you remember, it's the nonmetals on the right side of the periodic table that tend to gain electrons and become anions. Ionization energy, you guys, this is a big topic. The amount of energy needed to remove the least tightly held electron from an isolated atom. So basically, ionization energy is the energy needed to remove valence electrons. Guys, check it out. I don't know if you guys can see it, it's a little small, but let's just look at aluminum, for example. So you notice there's I1, I2, I3. That's just saying this would be the energy needed to remove the least tightly held one. I2 would be the energy needed to remove the next least tightly held one. I3 and so forth, right? You guys will notice, look, so for aluminum, the ionization energy 1, it takes 578, this would be, let's say, kilojoules per mole. I wouldn't worry too much about the units right now. That's how much energy it would take to remove aluminum's outermost electron. Then, the I2, it would require 1,817 kilojoules per mole of energy to remove the second least tightly held. And why you would expect the numbers to go up? Why? Right? Because as you're removing successive electrons, the next electrons are going to be closer to the nucleus, right? So would it take more energy? So it's not surprising that the amounts go up. And then its third least tightly held electron would take 2,745 kilojoules of energy. Now look at I4. Then it's 11,577. Obviously, you can see a jump. I mean, they obviously show it with the color code here. There's a big jump. Now, there's an increase in the amount of energy, the ionization energy, as you go from the first to the second to the third. But then there's a tremendous jump. Like this is jumping about maybe 2 to 3 times as much. This is it's jumping by 1,000. This is jumping by like 8,000. It goes from about 2,700 to 11,500, about 4 times the amount of energy. So the question is, what might account for the fact that it requires so much more energy to remove aluminum's least tightly held as opposed, fourth least tightly held as opposed to the third least tightly held? And I think a lot of you guys know, because if we look on the periodic table, remember this is the nice thing about the periodic table, they're in order, remember, of chemical reactivities, which is directly related to their electron configuration. If we look at aluminum here, hopefully you guys can see it. What this tells us is, guys, remember, it's got 3 shells of electrons, right? Because aluminum's in the 3rd period. It's got one, the inner shell is full, its second shell is full. So that's why when we do the electron configuration, we can just say neon. And then what do we show? The valence electrons. And what do we notice? If we count over here, 1, 2, 3, aluminum has 3 valence electrons. Once again, that shouldn't be surprising then. The outer 3 electrons are relatively easy to remove, but then once we remove the 4th one, the reason why that's difficult, because once we remove those outer 3, we remove the 4th one. Now that electron would be in the second filled shell. It would be in an inner shell, which is much closer to the nucleus and therefore much more difficult to remove. So, yeah, then just explain what we just said there. Okay, so ionization energy, it requires energy. Let's say energy is applied to a neutral atom. We can pull off an electron, then the atom becomes positively charged, right? Okay, left to right in a period, what do you guys think happens to ionization energy? As we go left to right in a period, does the ionization energy increase? Does it require more and more energy to remove the outermost electron, or does the ionization energy decrease? Does it require less and less energy? Guys, look, as you go across, the ionization energy, hopefully you guys predict correctly, hopefully you guys pause this and you're thinking about it, it increases. So you guys let's just look, why would it increase? I'm hoping you guys would recognize, well, wouldn't you guys agree? As you go left to right, don't we have an increase in the number of protons? If we have an increase in the number of protons, aren't those going to be holding the electrons more tightly, and therefore it's going to require more energy? So we can say an increase in the positive nuclear charge as you go left to right. And then secondly, what do you guys notice? The atoms are getting what? Smaller. So therefore, if they're smaller, wouldn't you guys agree the outer electron over here on fluorine is much closer to the nucleus than it would be in lithium? Closer together those charges are, the more difficult it is to remove. Now you guys, unfortunately in AP chemistry we have discrepancies, right? We like to believe that this is always the case. Notice it's called a trend. It doesn't necessarily, there can be deviations from the trend, and that's kind of what we're going to address. We never did in regular or honors chemistry, but we're going to have to show some discrepancies with that here shortly. Here you guys, we're going to see some Italian debaters. The Italian debaters. On the one side of the Italian, these are the Italian protesters. Provolone, provolone. She says, antipasto, antipasto. All right, deviations. So I don't know if you guys can see this, but they're kind of showing the ionization energy, and as we go from lithium to neon. So basically, you guys, for example, they're just showing in a period, lithium to neon. And you can see in general, what do we see? The ionization energy is increasing, right? But you guys will notice there's some slight dips here, okay? And so now I just want to kind of bring up what might explain why there's some slight dips. So for example, one is between group 2 and group A. It'd be between like beryllium and boron. So look, we got beryllium and boron between the second group and then this third group. So you know what? Maybe we'll just look at the the valence electron configuration for boron. Or here, we'll do beryllium first. Beryllium, it ends 2s2, and then if you go boron, it's 2s2, 2p1, right? Boron has 3 valence. You guys look at a periodic table, you guys will see boron has 3 valence electrons, beryllium has 2. So why would boron, even though in general, as you go left to right, doesn't it, we were saying in general, it requires more and more energy to remove the outermost electron. But boron is actually, it's actually slightly easier to remove boron's outermost electron than it is beryllium. And you guys see why? Because which electron is going to be removed from boron? Isn't it this one right here? From the 2p orbital, which is higher in energy, or you might even say further from the nucleus. It's going to be slightly easier to remove that than it is to remove one of those from that 2s orbital. So that can explain the slight discrepancy there. There's also another, so it's saying it's removed from a p orbital rather than an s orbital. All right, we'll just move on from there. Oh, and then they're saying another one is between 5 and 6. Okay, So we could look at, let's see. Sorry, guys, one sec. Let's say let's compare. So let's compare nitrogen and oxygen. Okay, so nitrogen, I'm going to do the valence electron configuration. It's 2s2, 2p3. Oh, you know what? Let's show this. Let's show it like this. 2s is 2p3. So it has 2 electrons here, and then it has 1 electron in each of these 2p orbitals, right? And then oxygen, you guys, right? It wouldn't be much different. It just has 1 extra electron. So wouldn't it be, right? It's just like nitrogen's, except oxygen has 1 extra electron, right? So it's there. So even though oxygen is further to the right, so we would have expected based on the trend it to be harder to remove its outermost electron. But in actuality, because like which one would be removed in oxygen? Wouldn't it be this one right here that's paired up? You guys, and which one would be removed in nitrogen? It's going to be one of these. We'll just say that one, right? But which one's easier to remove? Wouldn't it be this one? And you guys see why? Even though they're in the same same potential energy orbital, but this one is actually paired up with another electron. And what do electrons do? They repel each other. So this one will actually be slightly easier to remove than nitrogen. So that would explain why there is actually a slight dip in ionization energy as you go left to right. So just note some of those discrepancies, so those anomalies. Okay. Okay, you guys, top to bottom, what do you guys think? Does ionization energy increase or decrease? Is it easier and easier to remove the outermost electron, or harder and harder as you go down? Hopefully you guys remember, it actually goes down. So basically what we're saying here is, here at the bottom, it's easier to remove an electron from one of the heavier atoms down bottom than it would be at the lighter elements at the top. What might explain it? You guys just kind of looking at our diagram here, this is where this diagram really, I think, helps us a lot. Wouldn't you guys agree? Well, first of all, I don't, right? You have the screening effect again, guys, right? You've got more and more shells of electrons that interfere with the attraction of the outer electron for the nucleus. Remember, these are just positive nucleus right here, right? And therefore, wouldn't you guys agree, it's much easier to pull off that electron than it would be an electron, say from a cesium. If you guys are looking, you guys just showing you on the periodic table. Once again, it would be nice if you were in the class, I could just be pointing, you guys would be looking at the same periodic table, and I'm going to show you this whack one. Cesium, it's a lot easier to pull an electron from cesium than it would be from lithium. And then another thing you guys can see, what else is changing as you go down, guys? The atoms are getting bigger, right? So here, toward the bottom, isn't the electron further out from the nucleus than it would be right here? And therefore, if it's further out, it's not as tightly held, and therefore easier to remove. Increase in atomic radius. Okay, guys, last topic for today, electronegativity. That's the measure of the tendency of an atom to gain electrons. It's kind of like the opposite. Remember, ionization energy is the energy needed to remove electrons. Electronegativity is the measure of the tendency to gain electrons. So you have a neutral atom. Let's say it gains an electron. Doesn't that neutral atom become negative? And in this case, it doesn't require energy. Energy is actually given off. You guys see how this would be like an exothermic process, because energy now, the energy factors on the right side it's being produced, whereas ionization energy, required energy, that's an endothermic process. So from left to right in a period, you guys, let's just go left to right. What do you guys think happens? Does the electronegativity increase or decrease? Is there a greater and greater attraction for extra electrons, or less and less? Posit, think. It increases, but notice it says until the noble gases. Remember, the noble gases essentially have a 0 electronegativity. Remember, they're already happy, fat, content, stable. Their outer shell's already full. There's very little to no attraction for extra electrons. That explains why noble gases are pretty non-reactive. So until the noble gases, so basically we're talking the halogens. So in general, the electronegativity increases as you proceed to the right in the periodic table up until the halogens. So you imagine the halogens have very high electronegativities, right? And why might that be? Why would fluorine have such a much more higher electronegativity than lithium? Hopefully you guys can tell. Well, first of all, isn't there an increase in the nuclear charge, right? You guys remember, where are they getting these extra electrons from? Wouldn't they get it from adjacent atoms? So where would what would the electron be more attracted to? When you guys agree, this fluorine here that has, because what is it that's going to attract the electrons? It's always the nucleus. So if this has a greater positive nuclear charge, that's going to have a greater attraction, therefore it's going to have a higher electronegativity. And then also, what else do you guys notice? The atoms get what? Smaller. So when you guys agree, any adjacent electrons or electrons in an adjacent atom, wouldn't you guys agree they could get closer to the nucleus and therefore have a stronger attraction? So it decreases atomic radius. Unfortunately, guys, there are some anomalies again, so we want to show it. So in general, as you go left to right, electronegativity increases, but there are slight deviations to that. Now you guys will notice all these are called the electron affinities. You notice the values are all negative. You guys remember why that's negative? Because that's an exothermic process. What does the negative mean? It means heat energy is released when it gains electrons, okay? So realize that. But you'll see some deviations here. So look, so for example, lithium, if it were to gain an electron 60, it's not even, we won't even use units. And 60, we'll say kilojoules of energy is, look, it's negative is given off, right? So let's do the valence configuration for lithium, okay? It's 2s1, you have one electron in the 2s, right? Remember the valence, alkali metals have one valence electron. And then you guys, let's look at beryllium. Beryllium is 2s2, right? It's 2s1, 2s2. So, you think about it, okay, so now we're measuring the tendency to attract electrons. Well, if lithium's going to attract an extra electron, let's say an extra electron, where is the extra electron going to go? And you guys agree it's quite convenient. There's still space in that 2s orbital. It's going to fill that. But if beryllium is going to attract an extra electron, where would that extra electron have to go? Well, the 2s is already full. It'd have to go in the orbital of next lowest potential energy, which is the what? The 2p's. Now, you guys, what's more likely to attract an electron to the 2s or to the 2p's? When you guys agree, it's going to be to the 2s. And so this shows a slight deviation, right? We would normally expect going from left to right, there would be a continual increase in electronegativity, but there's actually a slight dip when you hit beryllium. Beryllium doesn't have as much a tendency to attract that extra electron as lithium does, because that extra electron would be further out from the nucleus, okay? So that's a deviation. And then there's another deviation if we look, look. But so apart from that, look, it goes negative 60, okay, it's slightly different, but then hopefully you guys can see in general, it goes from negative 27, negative 122, negative 141, negative 328. There's an increase. There's more and more energy given off by the attraction of electrons, right? But now there's a deviation here between carbon and nitrogen. Let's just try to see if we can explain why that might be. So let's just do the valence electron configuration for carbon. Carbon is 2s2, and then it's 2p2, right? Because carbon has 4 valence electrons. So it'd be like that, right? And then look at nitrogen. Nitrogen is 1 over to the right, so it doesn't have 4 valence electrons, it has 5. So nitrogen would have 1 electron in each of the 2p orbitals. Now you think about when they gain electrons, where would the extra electron go? So if carbon were to gain an electron, where would it go? Hopefully you guys realize when it go into this empty 2p orbital. And if nitrogen were to gain one, where would it go? Wouldn't it have to go into one of the 2p orbitals that's already occupied by an electron? Well, what's more likely, guys? For an electron to be added to an empty 2p orbital or to a 2p orbital that already has an electron in it? Wouldn't you guys agree? An empty 2p orbital, because we remember, what do electrons do? How do they interact with each other? They repel each other. So therefore, carbon would have a slightly higher electron affinity than nitrogen, even though it's to the left, as we would expect the electron affinity to constantly increase as you go left to right, but this would explain why there's a slight dip, at that point between those two values. So just recognize some of those deviations, guys. I know, guys, it's kind of a pain, but that's just how it is. I didn't create it. You guys complain to God. Okay? And they're just explaining what we just showed right here, so if you guys could follow what I did there. And if you guys want to write that down, you guys pause it, but I'm just going to go here a little faster. Oh, and lastly, you guys, from top to bottom. So what happens to electronegativity in general, guys, as you go top to bottom? Hopefully you guys realize it actually decreases. And what are the reasons? You guys should get this. Why is, let's say, cesium down here less likely to attract electrons than lithium up here? When you guys agree, once again, it's the screening effect. We have more and more shells, so therefore the positive nucleus's attraction for any extra electrons is going to be weaker, because you have all these underlying shells of electrons that are screening out it's a positive net positive nuclear effect on any outside electrons. And then once again, what do you guys see is happening to the size of the atom? Isn't it becoming larger? And therefore any outside electron would be further from the nucleus and therefore less likely to be attracted. All right, guys, good stuff. Glad you could stick with me. We'll see you next time. Bye.